several speakers, and each speaker has 20 minutes, and maybe because of several speakers, we will only have a couple of short questions after it. Yeah, so let's start from. Our speaker of that demonstration is so let's go.
Title of my talk is Physical Hamiltonian for Java and General Relativity. Can you hear me? Maybe I don't need to better? Okay. So the title is Physical Hamiltonian for Java, gravity, and general relativity. So first let's get to know Einstein's theory. In Wheeler's famous words, space-time tells matter how to move and matter tells space-time how to curve. Well, this saying has seeped into popular culture and public discourse. But with all due respect to Wheeler, whom I respect very much, it's the Hamiltonian which tells everything, including the metric how to move. Or, as a famous saying by Mark Twain, thunder is good, and thunder is impressive, but it's likely that does the work. Or, to paraphrase, geometry is good, geometry is impressive, but it's the Hamiltonian that does the work. So we want to go and look at Hamiltonian. So if you use the usual anomaly tensor Whistler decomposition of the metric, then you'll see that the standard Einstein theory will produce the canonical form, the Hamiltonian, which is basically a power system, a combination of constraints. So the whole Hamiltonian starts with constraints. And you have the super Hamiltonian constraint and super Hamiltonian constraint. And as we know, if your Hamiltonian is totally made of a constraint, then if you require Dirac condensation, and you see that the states actually don't evolve, they are frozen in time. Only that the matrix elements of the operators actually also do not evolve, whether you do it in Schrödinger picture or in the Heisenberg picture. So, but you may say, oh, that's the beauty of general covariance, but it's also a challenge of general covariance. Okay. So, apart from that, we know that general relativity has various technical difficulties. For instance, the non-renormalizability. Now, the proposal by Moshava is to give up all covariance in favor of three-dimensional differential invariance, and we should include higher spatial derivatives, but we don't include higher time derivatives. So we don't buy unitarity, but we have higher spatial derivatives to improve the convergence. And in a nutshell, the theory is in the canonical form. You reduce four-dimensional differential symmetry to three-dimensional spatial differential invariance. In canonical form, you also have this constraint. But Hamiltonian now includes various terms, and various possible terms you can include to have three-dimensional differential invariance. So many terms, but this is what we call the detail balance. It's a way to restrict the number of terms. And in the three-dimensional differential, you can have a deformation parameter. For Einstein's theory, this lambda is 1. But in this theory, you can have deformation parameters. And these terms are given by Chen-Simon's action and the Einstein-Huber action, and you can get this. And the point is that this will produce the Gordon-York tensor and the dimensions are together. And worry the Lagrangian looks like that. So Moshava gravity actually comes in two versions. You have the projectable one, where the constraint is the integrated Hamiltonian. Now, because you don't have a local constraint, so you have a lack of an extra constraint, so you may have extra degree of freedom due to a lack of local Hamiltonian constraint. Then there's the non-projectable one, where each x is just like general relativity, however, it's each of a different function. So, and this can be divided again into with and without detail balance. With detail balance, this without detail balance is more general potential. The point is that in general relativity, we know that the constraints will be the Dirac algebra. Note that this is not the algebra of four-dimensional differential invariance. This part here is three-dimensional differential invariance, but the other one is not. However, we know that on shell, if you impose the constraints and equation motions, then these constraints do generate E derivatives in the normal direction and also in the direction tangential direction. So they do generate on shell for the metric as well as momentum, the correct four-dimensional equal motion transformation. Now, conversely, it's also known that if you have the Dirac algebra, and if you have the Hamiltonian with the matrix basic variable, then it implies that this algebra, you can reconstruct general relativity and you get lambda equals 1 and so on, and potential Einstein do. But this program is also called Geometrical Dynamics Regained a long time ago by Washman, Kitash, and Heidenbaum. And so general relativity always the general algebra. Now, if you depart from the Dirac algebra, or you depart from general relativity, then it means that you have something which takes the place of Dirac algebra. But what takes its place? If you look at the case where you have just pure, no potential term, just this term, but you have lambda not equals to 1 in the supermetric, you see that it's okay. You get the closed algebra, but it's not Dirac algebra because instead of getting here, you get 0. Right? Now, however, if you now include the scalar potential, but you deform lambda, so it's not equal to 1, then you get the extra constraint. You get secondary constraint, and then you go down from there, you'll see that it gives rise to other conditions such that in the end, for lambda greater than 1/3, you have no solution. In Einstein's theory, lambda is 1. Exactly 1, you have Einstein's theory. Slightly less than 1, you have no solution. And suppose we look at now Hosowa gravity, where you have this, instead of just scalar potential, you have this lambda deformation here, and also this potential is not Einstein potential. That means this H is neither the supervector is not the form of geometrical dynamics, and the lambda is not equal to 1. Then the point is that actually you get some inconsistency. You'll see that all this tells you that basically you don't have a solution for this theory, and it's severely constrained and perfectly inconsistent. So the conclusion is that Hamiltonian constraint of Hosowa gravity in a non-projectable version with a local constraint is inconsistent. The projectile version with a global Hamiltonian constraint is consistent. There's no inconsistency. However, because you have lack of constraint, you may have extra scalar gravitons behavior. Now, the point is, whether projectable or not, the Hamiltonian of Hosowa gravity is still constrained to vanish due to take this or this, despite the fact that four covariance was not your sought after result. In fact, so that gives us the idea that maybe that's not what you want. Okay. Now the point is, because if you don't have that, then you again have this whole evolution and frozen formulation, formality. Is there a way out? And to have true evolution generated by a physical Hamiltonian is what I'm going to talk about. The subtle clue is that if you look at Einstein's theory carefully, there's a subtlety in the a posteriori physical meaning of the last function. Well, this is a priori arbitrariness. Let's look at what I mean by this. A priori, if you try to evolve this is arbitrary, this arbitrary. A priori, arbitrary. You get this. However, by the equation of motion, you will see that there's a result for this n, and this n is always given by this a posteriori after the constraints and equation of motion is solved. It gives you this meaning. In other words, if you look at n dt is much better. It tells you this how this log, the determinant of the tree matrix is changing. This is just the same equivalence task, the same three-dimensional equivalence, divided by something called h bar, which I will show that it's the Hamiltonian density of the physical Hamiltonian construct. So this a posteriori meaning, despite the fact that a priori is arbitrary. So now that means, in general relativity, if you look at this, it's the same thing as tell you that you get this result by evolving in general relativity. You get the a posteriori relation for n. So the Hamiltonian for general relativity can be divided into n. This h bar is exactly this term that I was referring to. And the point is now, we adopt this, which I'll call the physical Hamiltonian. And we don't have a Hamiltonian constraint, we have this Hamiltonian, and we dispense with the Hamiltonian constraint. The point is that if you go through this motion, you will see that this Hamiltonian produces for you the correct a posteriori value of the last function in general relativity. So it mimics general relativity by reproducing the correct last function in general relativity. So we have this Hamiltonian instead. And then this Hamiltonian is not constrained to vanish, it's a true Hamiltonian. And all of that, the change in the logarithm of the determinant of the tree matrix is actually decomposable into two terms. One of it is the global change, which is gauge invariant, and the other is actually can be gauge away. So the gauge invariant part of this is delta t. And you will see that delta t is actually the change in the logarithm of the volume of the spatial images. So in other words, if you are using this physical Hamiltonian, it will tell you how the universe is changing with respect to the change in how the wave function is changing with respect to the change in the volume of the universe. Okay, so that's a physical Hamiltonian. And the physical Hamiltonian looks like this, and it was this one which I put it. In Einstein's theory, this D is just a scalar potential and a cosmological constant. But now the point is that when you have this, you can now deform this potential so that you can deform it to the way. The advantage is that this will allow us to tweak and modify the potential without getting into inconsistency in the closure of the Cartesian algebra. And yet it uses the same dynamics in the limit when the potential is that of Einstein's theory. And then in the theory of Osawa, you extend this potential. So you get the physical Hamiltonian this way, and the one we suggest is this. And you see that quantum mechanically you want this repulsive definite. And you can do this by choosing this operator where you use the momentum operator the assignments of the Fi connection plus the Einstein over 3 dimensions, and you get this number of terms, and you'll see that this term actually contains the Einstein Hilbert term and the cosmological constant, and there are extra higher curvature terms, which are the traceless part of the Ricci tensor and the York conformal tensor, the square rings. So that this higher curvature derivatives are extra terms of Einstein's theory, and these terms are actually absent in frequent Robertson-Walker cosmology because of Robertson-Walker's pricing is conformally flat. And also you don't have a traceless part of the Ricci tensor because constant curvature. And also in black hole solutions, if you take the plane Leverrier-Gustafson slicing, which is a constant curvature slicing, they are absent. Okay? And not only that, they don't produce in those linearizations around these backgrounds, or flat backgrounds, they don't produce extra equation of motion because they are second order. So you have a delta of this and then a variation of this. So they don't produce extra terms when linearized about this constant curvature backgrounds. Going back to solutions. In the Hosowa gravity, you don't have 4 chlorides, so the numbers of the solutions are particular to how you slice it. So, for instance, if you take the plain Leverrier-Gustafson solution, well, you'll see that it is the exact solution of Einstein's theory plus this term also, because it has no contribution. So, it's the exact solution of this Hosowa gravity. Whereas the usual standard form is not the exact solution in Hosowa gravity. Okay. So, if you do this, and there's a difference. For instance, if you go through this, well, we know that there's a paper, it's selected for viewpoint physics, there's a paper with this real letters, which gives Hamiltonian, and you have a solution. And this solution is, we can check, is a solution of this complicated Lagrangian or Hosowa gravity, but it's not a constant curvature solution. And there's a difference. If you look at the difference, in the Einstein theory, you will get this. And in that one, in that particular theory, you see that different behaviors in the powers of R will come out. So it doesn't quite produce for you Einstein's theory, the results of Einstein's theory. For instance, this is what my student has done. In the one which you choose the constant curvature plane of Leverrier-Gustafson solution, you have the precession of Mercury, which is like this. In their theory, if you really plot it out, you'll find that their theory predicts something like this. Okay. Now, despite the fact they are chosen for statistical review, okay. So this is something I wish to talk about. Now, so to go back and summarize, the Hamiltonian which we suggest is this. And in this theory, Hosowa theory is extension of Einstein's theory. There's no inconsistency in the algebra, and this is a Hamiltonian that causes evolution with respect to a time, which is the logarithm of the volume of the universe, and this theory is 3-dimensional equimotion invariance, and so that you firstly have realized this by using an extension of Einstein's theory, which 4-dimensional symmetry is not a fundamental property of the physical world. And that's the answer. Thank you.
Question? Comments? So if not, that's the second speaker again. So next speaker.